Good afternoon, everybody. First of all, I'd like to thank the Asahi Glass Foundation for inviting me to this lecture and, of course, for awarding me the prize, the Blue Planet Prize, yesterday. So it's a pleasure to see also a number of colleagues I've met in Japan before. I'd like to, in particular, also welcome some members of the Tokyo-Yokohama German School. Now I switched to German, and I can test whether you really belong to that school. Ja, ich freue mich, dass Sie hier sind. Könnten Sie mal Ihre Hand heben, wer hier dabei ist? Herzlich willkommen, ich freue mich, dass Sie hier sind. Ich werde leider in Englisch sprechen und nicht in Deutsch, aber das ist, glaube ich, auch okay. So, thank you very much. My lecture is about, you see, the big picture of planet Earth. So I could have talked about certain impacts, but I really like to provide you with a journey through space and time. And I'm focusing on the two main elements that in a way are shaping our reality, that is ice and fire. Because this planet has moved through ice and fire many times, and we are now able as scientists to reconstruct that, to go back billions of years actually. And the question is, will we move back to the ice, or will we go right into the fire? And the jury is still out, so I'll try to show you how the dynamics has developed. So let me start by showing you a picture of our galaxy. Do you know where planet Earth is? Gretchen, you should know. Okay, I'll show you. That's about the position of planet Earth in our galaxy. The question is this the only blue planet in the Milky Way or even in the universe? So what do you think, how many Earth-like planets are there in our galaxy? So this is a field of science I have dealt with for a few years, actually, I published work on that. So, how many Earth-like planets are there? And you must know that 15 years ago, we had no direct evidence of extrasolar planets at all. Now, with the Kepler telescope, we are able to detect them. And actually, the answer is, within our galaxy, tens of billions of Earth-like planets, at least 20 billion ones, only in our galaxy. Now the next question is, if there are so many Earth-like planets, did they develop life, maybe even intelligent life, even a technical civilization? No? So the question is there intelligent life outside Earth? I often ask myself, of course, when you refer to the doomsday clock, which was shown by the chairman, whether there is intelligent life on Earth. You cannot be sure. But now the question, how many technical civilizations are there in the Milky Way? And this is the famous Drake equation. No? The Drake equation just tells you, if you start from, let me see with it, yeah. So this is the number of technical civilizations currently existing in the galaxy. So you start with the total numbers of stars in the Milky Way, which we can calculate, so it's hundreds of billions actually. When you multiply it with the fraction of stars that have planets, and actually we know now on average it's 1 or 2, fraction of planets that are Earth-like and are in the so-called habitable zone. That means the planet should not be too close to the star, because when it's too hot, and it should not be too far away, because when it's too cool. so like Venus, Mars, and Earth in our solar system. You multiply it with the fraction of planets, habitable planets, that actually develop life. And this seems to be something quite common because simple life developed on Earth already 3.5 billion years ago, at least, probably even earlier. So that seems to be something that just emerges if you have the right conditions. But then come the hard factors, the fraction of habitable planets that develop intelligent life. And this only happened in the last minute of the Earth history, so probably, let's say, 7 million years ago. Finally, only in the last 2 centuries on Earth, a technical civilization was developed based on the Industrial Revolution. So you multiply it all and all and all, and finally you have this factor here. This is the most important of all. Because if we ask currently how many technical civilizations are in the galaxy, then it depends crucially on the mean lifetime of a technical civilization. Is it 1 million years, or is it just 200 years? We cannot answer it now, but there is one indication that this last factor is not very big. So there is a book which I like very much, written by Paul Davies. It's called The Eerie Silence. And eerie silence means a very strange silence, because since 50 years there is a so-called program for listening out into space to receive signals from extraterrestrial civilizations. So it's called SETI, the Search for Extraterrestrial Intelligence. And for 50 years we haven't heard anything. No signals, only silence. Although, as I told you, there are probably at least 20 billion Earth-like planets in our universe, in the galaxy, and many more in the universe. So why don't we hear anything? Because maybe the last factor here is very small. The average lifetime of a technical civilization is small because we may destroy ourselves through a nuclear war or by environmental degradation. So we have to be very, very careful. Now I'll talk about how nature, as we know it, has emerged on this planet, and it was a journey through ice and fire. So what is not so well known, 750 million years ago, for example, the planet was freezing completely over, called Snowball Earth. And you see, this is how it happened, more or less. You have, in time, a development, so you have a cooling here. The temperature dropped by 80 degrees centigrade, and then finally recovered because of the volcanoes, spit out CO2, and finally the ice was melting again after probably 1 million years. The planet turned very hot and then finally settled like this. So this happened twice in Earth history. And it was a combination of solar insolation, radiation, and CO2 concentration in the atmosphere. Now, something very interesting, a colleague of mine at the Potsdam Institute has just published a paper. All the fossil fuels we burn, in particular coal, that were fueling the Industrial Revolution, they were formed in the Carboniferous and the Permian period, so between 400 million years ago and 250 million years ago. So without that formation of coal, we could not have started industrialization. Also oil was formed and gas. Now the funny thing is, and the really amazing thing is, that coal was formed by plants which died away, and the debris was covered by water, and so finally it was not reoxidized again. So carbon was extracted from the atmosphere and turned into coal in the end. But if you remove carbon from the atmosphere, the CO2 concentration drops. And it approached almost 40 parts per million, that means that would have been the critical level where the next Snowball Earth episode would have happened. So the coal, which we burn now in order to heat up the planet, almost implied that the planet was freezing over. So you see, this interplay is really fascinating. Talking about ice, the biggest ice sheet on Earth is the Antarctic ice sheet, as you know. When did it form? Well, this was about 35 million years ago. So this is in temperature. Here is the Antarctic glaciation. It happened for various reasons, actually. One reason is that the Indian plate sort of crashed into the Asian plate in order to fold up the Himalayas. And these mountain ranges were increasing weathering with this withdrawal of CO2, for example. Also, the Drake Passage opened, which is separating the Antarctic continent from South America. So the ocean currents rearranged. It's a fascinating story. In the end, there was this glaciation of Antarctica. In between, there was a thawing again, Antarctic thawing, and then finally we go into the ice ages, and then we have the big Antarctic ice sheet. Now let me move on in time. So over the last 2.5 million years, we had this permanent change between ice age, glaciation, and deglaciation. Currently, we are in a warm age, of course. Now, together with colleagues, we were able to solve, if you like, the riddle of the ice ages. Why do the ice ages come about at all? And this is the answer, which is very hard for you to understand, but I'll explain it a little bit. It all depends on the CO2 level in the atmosphere. So, for example, this is going back in time from today, 800,000 years ago. And it turns out there is a simple function here, you can see an exponential function, which is relating insolation, the strength of the sun, the insolation on the northern hemisphere, together with the carbon in the atmosphere, the CO2 concentration. Now, look, here is the critical function. That's the black line. And if the real CO2 is falling below that line, here, if you have a crossing of the black line and the blue line, then you will have an ice age. And number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last 10 ice ages were triggered by a transgression of the CO2 concentration below a critical value. And this simple function tells you precisely when the last 10 ice ages happened. And we have the geological record. So we came up with that function and we tested it with the data, and it's correct. So this is a major breakthrough. Now the really interesting question is, will there be another ice age, and when will it be? We can now do a sort of election procedure. I could ask you, when is the next ice age due? Tomorrow, next week, 10,000 years from now. But unless you fall asleep during my lecture, you will hear the result and the answer a little bit later. So let me move on. During the last ice age, now we are back to, let me see, 100,000 years from now, before today. Yeah? So these are the temperature on the northern hemisphere, and the Earth was moving through this space wildly. So you had changes in global mean temperature of 10 degrees within a few decades, actually. Finally, we have entered the so-called Holocene 11,000 years ago. And you see, compared to the wild fluctuations of the last ice age, we have an extremely stable climate. This is why agriculture was invented, the so-called Neolithic revolution. It was only possible in an extremely stable climate. We may change that now. Why does the climate change at all? And you have heard already, CO2 concentration, insolation is important, but now I show you the details about it. So one thing is purely astrophysical parameters. So the orbit of the Earth around the Sun is changing in shape. The axis of the Earth is tilted more or less, actually. And finally, like with a children's toy, the axis can spin around a sort of median orientation. And this is happening because planet Earth is not only encircling the Sun, but it's also influenced by Saturn and Jupiter, so it's all gravitation. So depending on what type of orbit we have, currently the Earth's orbit is almost a circle, a perfect circle, but it will become more eccentric in the future. So depending on what these parameters tell us, we will have more or less sunshine on the northern hemisphere, and that is very important whether, for the question whether an ice age starts. And the other thing is, so this was Milutin Milankovitch who published this in 1941, the famous Milankovitch cycles. But the other factor is clearly the greenhouse effect. You heard about it. CO2 in the atmosphere is trapping, if you like, heat. And the more CO2 you have, the thicker the blanket is, and the more the planet warms up. And this theory was, for the first time, developed already in 1896 by Svante Arrhenius, a famous Swedish scientist, a Nobel laureate in chemistry, by the way, also, who single-handedly calculated with a pencil and a stack of paper the greenhouse effect. And he already calculated back in 1896 that if you double CO2 in the atmosphere, you will have a warming of about 3 degrees. And this is still the best value we have with the most advanced computer models. So this was one of the ingenious feats in science. So if you put the two factors together, you know why the Earth's climate is changing. Now, we cannot do anything about the orbital parameters. So this is pure physics. Gravitational pull will happen just as it is. But we can change the concentration of CO2 in the atmosphere. And I show you now how the Industrial Revolution came about and how it all changed. And this is what I call the sea story of human civilization, not the history, the sea story, because it's about the output of CO2. And you will see in the active regions where the Industrial Revolution started, it all started in Lancashire in England, you will see, according to this color coding here, how much emissions or how many emissions were released and how the planet actually changed in CO2 concentration. By the way, you have to notice that this is an exponential coding. That means whenever the color changes, you multiply the emissions by a factor of 10. So here you have times 10, times 10, times 10, and so on, 10 times actually. So let's start this movie. It starts in 1751, and pixel by pixel, you will see the emissions from the Earth's surface. And of course, England and Great Britain is ahead of the rest of the world. So you see the rest remains black, and here the color is already changing into yellow. And you could even see in the first row London as an orange spot. Who is next? Germany. So the Industrial Revolution was entering the continent in Germany, and the third country was Poland. And the Polish are still obsessed with coal. It's a long tradition. And now you can see how it develops across the Atlantic, the eastern part of the United States. Coal was adopted and emitted clearly after burning. But look around, you cannot see Japan, you cannot see Australia, it's all black. Only after, through the British Empire, steam engines and so on were exported, you will see a color coding somewhere else, and the next country will be India. So it happens now. And you see also here New South Wales, Eastern Australia is appearing on the map. Argentina will follow a little bit later. And this is what we call the Victorian age, and in German you would call it Gründerzeit. So this is where industry, technology accelerated. But this also meant that you had two competing carbon powers in the world, namely Germany and England, still ahead. You see it's already turning red here. We are here on the color coding, but Germany is catching up. And this led actually to the First World War. The two dominant carbon powers were clashing, but the war was decided by the third carbon power, the United States. But now you see that Japan is catching up. And Japan will enter the Second World War. It will be the second clash between carbon powers. It ends now. And now the era of globalization starts, because now cheap oil is available. The Allied countries had access to cheap oil in the Middle East. And this is the era of globalization. Now you see how the world is becoming colorful, and almost every corner of the planet is emitting CO2. That means is using steam power, diesel engines, cars, automobiles, and so on. And finally, here, a big carbon power is rising, which is China. These are cumulative emissions, so China is now catching up. Within 2 decades, it's catching up with merry old England, for example. This is the map of the world in terms of emissions in the year 2013. This is how the Industrial Revolution came about and spread all over the world. And of course, you could ask, if development in a conventional way goes on, the whole world would turn red, actually. Is this what we are aiming for? The rising CO2 concentrations here were completely echoed by the rise in temperature. You see here, this is 10,000 years ago. You had in the Holocene only changes of 1/10 of a degree, and this spike here is directly caused by this spike here, the CO2 spike. Now the answer to the riddle of the ice age is, when will we have the next ice age? Well, it should only happen here. The next crossing of the blue line and the black line would be here in 50,000 years from now. But because of the CO2 we have already introduced into the atmosphere, you rather have to follow this line or this line. So I will blow it up, but you can see it in detail. So we have already introduced 500 gigatons, billion tons of carbon into the atmosphere extra. So you see these lines only touch, and if we introduce more, and we are on the course of introducing more, it will be the red line or the brown line. So there will be no other ice age. There is no crossing, and we have suppressed, as a planetary force, the ice ages forever. This is already happening. So if people say, oh, we are so small as human beings, we cannot influence the global environment, this is not true. We have already influenced it without knowing it. So clearly global warming is going on. This is now the recent record starting in 1880, instrumental record. You see global warming goes up like this. And people are very concerned. So this is the Paris Agreement, keep global warming well below 2 degrees. Why? Well, it has to do with the tipping elements in the Earth system. So I came up with this map a while ago at a lecture at Oxford University. These are the vital organs of the planet, if you like. The ice sheets, the currents in the ocean, the monsoon systems, the big ecosystems like the Amazon rainforest or the tropical reefs. And it simply turns out that if you go beyond 2 degrees, most of these elements will be pushed into a new state, and some of them will just be killed. The coral reefs, for example, the tropical coral reefs, will not survive a 2 degrees warming. That is why in Paris people ask for a 1.5 degrees warming only as the limit. So I'll skip that. I'll show you a few examples talking about the ice, what is going on. On the West Antarctic ice sheet here, you see already signs of collapse. This is the Larsen Sea ice shelf, a huge iceberg split off just recently. And this is another piece in Pine Island Glacier. And this is important. This is ice from the ice shelves, so it swims on the water, so it does not contribute if it melts to sea level rise. But look what is happening if you remove that plug. If you remove the plug, for 10,000s of years, the inland ice will be destroyed. So it's like you have a number of bottles and you uncork them. You pull the plugs. And there are many of these bottles around Antarctica. And we start on pulling plug and plug and plug. This is the one which is pulled right now. Greenland Ice Sheet, it's a similar thing. And this is very important because if the Greenland Ice Sheet melts, it will heavily affect the currents in the ocean. This is a simulation of the currents. It's a beautiful simulation. For example, here you see the Gulf Stream. You know the water is heating up in the Gulf of Mexico, goes through the Florida Strait and then moves towards Europe. And here in Japan you have another very important current, the Kuroshio current, which will appear after a while. Now we are moving around the Cape of Africa, and then we finally will move into the Pacific, where you see all these eddies moving around the equator. And finally, if we go through the Strait of Malacca, we'll finally enter the Pacific, and we will reach Japan. And this is the Kuroshio current. If the current is transformed and will create huge bulges, like it happened last week, actually, the great meander of the Kuroshio current, fisheries will be impacted, but the climate of Tokyo may be completely transformed. And this will happen if Greenland ice sheet melts, because when the sea level will rise by 7 meters, but also the ocean currents will be reorganized. So let me catch up. This is, if you like, the map of the Earth. And you have to take a minute to understand it. So, this is the timeline, 20,000 years ago, last glacial, 1900, today, 3,000 years. So that means 1,000 years into the future. This is how the temperature developed over time. So we were rising from the Ice Age. It was just 3 degrees cooler, the present interglacial, and these are the various scenarios for the future. So if everything goes right, we will keep global warming to just 2 degrees, and we probably will preserve most of the big ice sheets. But much more likely is that we will either move to a hemideglacial, where the complete northern hemisphere will be ice-free, or even the southern hemisphere as well. You could call it the global deglacial. This is the business as usual curve we are on right now. And this would mean we would move into the fire. These are pictures from California, north of San Francisco. You had the wildfires, Sonoma County, and so on. Just a few days ago, the same happened in Spain and Portugal again. And this is only at the local level, where Gretchen Daly is much more knowledgeable than I am. But this is a global map, for example, about the physiological limits for the human body. This means it's the so-called wet bulb temperature. It's simply the combination of humidity and temperature where you cannot survive without an air condition. So you cannot just survive in the open. And the color coding means how many days in the year would be critical in terms of your physiological survival. And wherever it's turning red, and the region you can see here, under business as usual, you cannot live in that region anymore. This is solid science. It's not a sort of a horror scenario. It is what the models predict. So in this region, in this region, in this region, and so on, you could not survive without artificial cooling. So, what can be done about it? Well, the scientists, of course, can only provide scenarios and provide warning. Decision makers and even religious leaders have to remind us of our responsibility for preserving the Earth. So I had the honor, as I mentioned yesterday, to present Pope Francis' encyclical to the world in June 2015, before the Paris conference. It was called Laudato Si. And this was a meeting of the Pontifical Academy in Rome last November, where Pope Francis reminded us that we as scientists, and I think that's appropriate for the Blue Planet Prize, of course have to discover, uncover, pursue the truth. We have to come up with the scientific evidence. But we also have to communicate it to the world. And as I showed you, this world is on the brink of collapse. So in order to preserve it, we have to remind ourselves this blue planet is the only planet we have. This is the picture. Thank you very much.